Right. Thank you for coming back. Right. Let me continue again what we have done just now. Right. We try um, to represent right the kinematic description pictorially and in mathematical form. Right. And then we have in mathematical form for velocity vectors, it can be written in this format. Right, just now we have the vr and v theta, and then we have x dot and y dot for Cartesian. So we have spherical polar and we have Cartesian coordinate system, right? And you can also write the kinematic description, the velocity description in the s coordinate system as well as in the normal tangential coordinate system. Okay, now about the here before I go to the acceleration, this is the way how we can draw the velocity vectors. It should be at the centers of the position, right? Center mass, and then we should have arrows, right? So from this figure, you have very long distance from one picture to another. They are taken at the same duration, right? So this one represents that the velocity is much more higher. But as you go to the top, the distance between the two images are very close. It means that the velocity is reduced, right? So this is what it means that the fluid, the particle is decelerating. The ball is decelerating, and then after that, after it's fall down, uh, we have acceleration as the ball going down, and even though the velocity here is zeros, but it still have acceleration, right? And then the acceleration will be the gravitational acceleration, and then the velocity is increasing over time until it reach to the floor. Right. So I just want to show it to you. Um, the quantities involved, right? Let's say we have the initial start at 0 second and the final time will be 1 second. So here we compute the average velocity. So we have the distance. Let's say this one in S coordinate system, but we not write in the S coordinate system, but in R, distance from a certain location, and then from that we can get the average velocity. And this is the way that we can define the velocity and acceleration in S coordinate system. Normally you use this S coordinate system for particle, right? This is the velocity. You have the distance traveled divided by time, and then we have the velocity divided by time. The velocity change with time, and then you get the acceleration along the S coordinate system. So here we use these two equation and form a system of equation so that we can write the acceleration not in terms of time but in terms of the distance and the velocity, right? So so that you have three equation that you can use to solve the magnitude of the kinematic properties. Now we can look at the this one represent the instantaneous kinematic properties, right? So we have instantaneous velocity and instantaneous acceleration. Right, so now we are looking at this nickel polar coordinate system. Right, so for this nickel polar coordinate system, right, we have again, I'm going to remind you, this is the way that we define the coordinate system, right? So let's say this one is R, and then we have the angle that we create from the x-axis, and this gives you the positive values. So here we say that the r is a function of time and a function of the angles, right? So now when we want to evaluate the radial velocity, right? So this one is radial velocity. So it says that this radial velocity does not the angle does not change with time, so that we consider only the right hand part of this equation, right? So we just consider this one only, and we remove this term, right? Oh, my goodness, right? So we remove this part, so we just evaluate the needs to represent the radial location. So if you want to draw the velocity vector for ni, right, let me use a different color there. So this one represent the r dot, right? I hope you understand. And then what about the accelerations, right? I just consider the r direction first. So for the R radial component for accelerations, there is another terms there that says that the radial will be there will be the second derivative of radials, right? So we're going to show the physical meaning of this thing in the exercise, right? So we have a component of radial acceleration. Now we're going to look example when this value will be 0, right? Right. So if you have, let's say we have a cylinder here, right? And we have a point P that has a rotational motion along the axis of this disc. So we have this r dot is equal to 0. It means that the position vector does not change its magnitude in the radial direction, so that it becomes 0. So if I draw it here at any location, right, at any instant, the value of RP is maintained same. So there is no change of uh, radial ni with time. So it means that when you make a second derivative, the value will be 0 too, right? So so if we have the like bicycle motion, right? So we have r dot equal to 0. So there will be no component of radial acceleration in that case. The radial ni what color is that? So we have that will be the r dot, and then we have the VR there, right? V theta there, and the angle is measured from the axis. Oh my goodness. So so normally we have R first, and it may always make a 90-degree angle between the radial direction and the angular direction. Radial direction, let's say this is the origin O, uh, right? So this R E R, let me make it bigger. And then we have this component in R directions, which is along the R direction, right? And then we have the tangential direction, something like that. And the coordinate that we use is measured from this horizontal line up to the So this is the notation. Anywhere that you go, this will be the orientation. Right, any question? So I give you 5 minutes to ask question.